Good morning, everybody. Today we will see how we can complete 6 electronic circuit analysis experiments using NI Multisim. So first, let us start with the common emitter amplifier. So usually the common emitter amplifier circuit, we are making use of voltage divider bias. So let us start constructing the transistor in voltage divider bias. So let us start with the transistor. So here I hope you are able to see my mouse pointer. So this is the transistor. I am clicking on that. And then here we have to type BC107. Then let's select this. I have double clicked on that. We got the transistor. Let me place the transistor here. Then let us go for resistors. Basic. We have to select, we have to click on this, we have to go for basic, and then we will go for resistor here. Then we will first, okay, let us take 4.7 is already selected. Let me go for that 4.7, which is the collector resistor. So I'm placing it here. Then let us go for 1 kilo ohm. So I'm selecting 1. Double clicking on this, Control R for rotate, then I am placing it here. Let us go for 100 kilo ohm. So I am changing this to 100, double clicking on this. Again, Control R. Okay, so let me do that again. We will go for this resistor here, 100K. I'm double clicking on this. Then we'll go for Control R for rotate, then I'm placing it here. Then let us go for the last resistance, which is 10 kilo ohm in the voltage divider network. Again, Control R. Then let us place the resistor here. Now let us go for one more resistor. Let me select 1 kilo ohm. I'm clicking on this, or we can click OK here. We got the resistor. At the input side, let me connect one resistor. Okay, let me place it here. Then one capacitor at the input side, so basic. Then we will go for capacitor. And let me select 10 microfarad. So you can type 10 followed by U. 10 followed by U. Then you can double click on this. We get the 10 microfarad capacitor. And then let me place it here. But here we have to select the electrolyte capacitor. So once again, let us do that. I have clicked on escape. Then we will go for capacitor electrolyte, this one. And then we are typing here 10U, so which represents 10 micro. Let me double click on this. We got the capacitor. Let me do Control R twice. Control R twice, and then let me place the capacitor here. One more capacitor at the output side. So the same value 10 microfarad. Let me click on OK. Then let me place it here. Then we need one bypass capacitor, 100 microfarad. So I'm changing this to 100. We can double click here. We got the 100 microfarad. Control R for rotate, and then let me place it here. Then let us go for the supply VCC. So for that we have to go for sources, power sources. Here we have VCC. Then you can click on OK. You can place the VCC here at the top. Then let us go for ground. Same power sources. We have ground. Let me click OK. Let us place it here. Now let us go for the input voltage source. So for sources, in the sources, we have to select signal voltage source, this one, then the AC voltage, and let's click on OK. So this is the input voltage source. Now let us start connecting. So I am closing this dialog box, and then connecting is very simple. Click here. Then we'll go and we'll click again here. I'm clicking on this, and then we will connect that one here. Then let us change this value to 12 volts. So this is 12 volts. I'm clicking on OK. You can rearrange this. For example, this VCC is not arranged properly. You can click on this and select it, drag, and then you can place it here. Then let me join this one here. Let us join this here. Then let us join this one here. And then let us join this point here. This one here. And then let us join this one to ground. Again, this point to ground. This capacitor appears in parallel with the emitter resistor, which is 1 kilo ohms. So I'm connecting the top there. Here, connecting the bottom here. Then let us connect the input source. Let us connect this here, then this one here, and then this point let us connect here, and let us connect this capacitor here. So this is our CE amplifier, common emitter amplifier. The values of these resistors are such that the transistor is operating in the center of the active region and the slope of the load line is such that it provides amplification. Okay, so all these are responsible for that. And then this particular capacitor is bypass capacitor. So for AC point of view, we do not need this resistor, whereas for DC point of view, we need this resistor. It increases the stability. So to make such arrangement, we are putting this capacitor. For AC signal, it will act as short circuit. So as good as no resistor, direct connection, emitter to ground. For DC signal point of view, this resistance appears. Fine. Then we are using these two capacitors, one at the input side, one at the output side, C1, C2. Those are blocking capacitors. They block the DC from entering the input side or output side. And I hope all the viewers know that capacitor blocks DC. Then let us see the input and output signal. For that, we have to select the oscilloscope. Let us go towards the right side. And here we have different equipment. Let us go for oscilloscope. So this fourth one here is the oscilloscope. Let us click on that. And then I am bringing this one here and one more click. Let me click it here. Now this has two channels. Always the second one goes to ground. So let us do that first. The second terminal, which is the negative terminal, has to be connected to ground. The first terminal A, let us connect at the input side. So let me take this, one more click here, then let me join it here. So now this channel A is connected at the input side. Let us connect the channel B. So one click here and then another click here. So channel B is connected at the output side. So to differentiate the input and output signals, what we can do is, let me double click on this wire and let us change the color of this. Okay, so you can click on this and then, for example, say input, let us give green color. Okay, so I'm selecting green color. Let us click on OK and then one more OK here. So here you can see that the input wire has changed to green color. Let us also change the output. So I'm double clicking on this. Again, we are clicking on this one. The output, let us put it as red. So let me select this. Okay. This one, and then let us click on. Okay, the already output is red. So let me choose another color. So let us say blue. Let us take this blue and let me click on OK. And then one more OK here. So the output is changed to blue color. Now what happens because of this is the input signal will appear in green color, the output signal will appear in blue color. So let us simulate and check that. To simulate that, let us click on this. So I have clicked on that. Then let us double click on the oscilloscope to see the waveform. Then you can click on reverse if you want a white background. Now we are able to see the waveform. So let us stop this. I have stopped the simulation. Here usually the input that we give is a very small voltage. So let us double click on this. Let us change this to 20 millivolts. So I am typing 20 here. Then we are changing this to milli. So the bottom one I have clicked. Once more I am clicking, we are getting milli. Okay. And then let us click on OK. Then let us run this again. Now we are getting the input and output waveforms, but we are not able to see it properly. So what we will do, let us stop the simulation. I am clicking on this. Let us move the oscilloscope to the center. Then what you can do, you can click on this. You can adjust this one. So here the waveform is increasing in its size. Let us click on this one. Again, let us adjust this. So we can see the input waveform changing. Let us also adjust the time base or times per division. Now here we can see both the input and output waveform. So all we have to adjust is these three. And you can put this in AC mode, even this one in AC mode. So if there is any DC component level shifting, it will adjust accordingly. So here we have given green color to the input. So this is the input, right? And we have connected it to channel 1. So a very small voltage in millivolts, whereas output we have in the order of volts. So this indicates that there is gain and there is amplification, and I hope the viewers already know that CE amplifier gives a phase shift of 180 degrees, which means whenever the input is high, the output is low. And this is what exactly we are getting, and this is acting as an amplifier. Now let us find out the bandwidth of this particular CE amplifier. What is the maximum gain? What is the bandwidth? How can we do that? We have to close this, and then we have to go for simulate analysis, then AC analysis. Here the settings you can put, okay, start frequency 1 Hertz, stop frequency you can give 10 gigahertz. Sweep type it says decade, we can leave it as it is. Number of points per decade 10. And usually we plot the graph in similar graph sheet, taking the y values in decibel. So we are changing the vertical scale to decibel, and then we can go for OK. Next, we have to specify what are the input and output variables here. So for that, simulate analysis, AC analysis, we go for output. We have already given this frequency parameters. We click on output. Then here, let us see what are the output variables. So V6 is the output voltage. You can clear whatever you have already. I am clicking on this. I am clicking on remove. Then let us identify that here the output is V6 and input is V4. Input voltage is V4. So the gain will be V6 by V4. So let us go for add expression. Let me click on this, and then V6, double click on V6, double click on divided by, then double click on V4. So V6 by V4, you can click on OK. So we got this one here, V6 by V4. Let us check that once again. So V6 is the output voltage. Then V4 is the input voltage. Gain is output voltage by input voltage. Okay. That is the reason we have taken V6 by V4. Then let us click on OK, and then let us go for simulate. Right. So this is the frequency response graph. And we know that the general shape is, as you increase the frequency, the gain in dB increases, then it remains constant over a range of frequencies, then again it reduces. So we are getting it as per the requirements. Then what we need to do here to find the bandwidth is we have to go for cursors. So you can click on this one. It says show cursors. So you can click on this, right, until you get the cursors. Now let me zoom in and see what are the cursors that we got. So I'm zooming in here. Let us see the cursors. So I'm clicking, I'm moving the cursor. So here I hope everyone are able to see there is one which indicates first cursor, then two which indicates second cursor. How to find bandwidth is we have to do maximum gain minus 3 dB. So first let us go to maximum gain. So go to next Y max towards right. I hope everyone are able to see the arrow direction. So this is pointing towards right, this is pointing towards left. We are here. The maximum gain is towards the right. So let us check that. I am zooming out. So gain is increasing, remaining constant, decreasing. So maximum gain is towards right. So once again, I am zooming in this one. And then we are going to the second cursor, right click, set Y value towards, go to next Y max. Okay, we are going to next Y max, so maximum. So it will adjust, the cursor will adjust itself at the point of maximum gain. Maximum gain minus 3 dB we have to do. So again right click on this, then go to, we have to set, now we have to set Y value. Okay, Y value, and I hope everyone knows that bandwidth is higher cutoff frequency minus lower cutoff frequency. So second cursor has to be placed towards higher cutoff frequency, which is towards the right. So that is the reason we are right clicking on this. Set Y value towards right. This is towards right, this is towards left. So we have to select this one. And then this is the maximum gain. So minus 3 we have to do. 36 minus 3 will give us 33. Okay, so we are changing this to 33 and we'll click on OK. Now the cursor tool has placed itself at the higher cutoff frequency point. Now what we will do is, let us do the same for the first cursor. So we are right clicking on that, then set, before that what we will do, we will go to next Y max, which is towards right. So the cursor came here. Now the lower cutoff frequency is somewhere here. So right click on this, Y value towards left. So let us select this one. We are at the maximum gain point. We have to do minus 3. So 36 minus 3 gives us 33. Let us click on OK. Now the cursor has placed itself at the lower cutoff frequency points. Now let me zoom out at this point. So here cursor 1 has placed itself at the lower cutoff frequency, cursor 2 has placed itself at the higher cutoff frequency. Now how can we find the bandwidth here? From this values that we have in this box, we can find the bandwidth and the maximum gain. Maximum gain we already remember that it is 36. We have already seen that. Let us find the bandwidth. So let me zoom in once again. So we are zooming in. Let us see this box that we have here. So the dx gives us the bandwidth. Dx is simply x2 minus x1. So this is x2 at higher cutoff frequencies. Remember, x-axis has frequency. So x2 is higher cutoff frequency, x1 is lower cutoff frequency. So x2 minus x1 gives us the bandwidth, which is dx. Okay, so bandwidth is 1.1266 megahertz, and maximum gain is 36.7204, which we have seen earlier. Okay, so this is how we can complete CE amplifier. We have seen both the input and output waveforms, and then we have obtained the frequency response here, and we have found out what is the maximum gain in dB, and then what is the bandwidth of this particular common emitter amplifier. Now let us see how we can convert the circuit which we have just simulated into a current shunt feedback amplifier circuit. So first let us close this graph. We have the circuit. To convert this into current shunt feedback amplifier, all we have to do is we have to place a resistor from base to emitter. So let us go for resistor. I am clicking on this, and then we'll go for resistor here. Let us take say 2.2 kilo ohm. 2.2 kilo ohm. Let us click on this. Okay. Let me place it here. So we have to connect this one between base and the emitter terminal. So I'm closing this one. Let us click on this. Let us join this one to the emitter, and this end let us join to the base of the transistor. Okay, so very simple. Our current shunt feedback amplifier is ready to execute. So now let us first see the waveforms. Let us run this one. Okay, let us run this, and then let us double click on this. So we have the input waveform. Let us stop this one. I'm clicking on this. Then let me change this. Here, due to the feedback, the gain is very less. So let us increase this value. So let me change this 10 times more. So let us put 22 kilo ohm. I'm clicking on OK. Now let us run. So now you can see that the output is very high. Let me stop this, and then let us change this one. I'm increasing this. So here you can see now that the gain is very high. Input we have given in the order of 20 millivolts. Output we are getting in the order of 500 millivolts. So there is gain. So what we have actually observed is the gain is comparatively less when compared to the previous case. Without feedback, the gain was high. With feedback, the gain has reduced, and that is in accordance with the theoretical concept. And here you can try various resistances. We have earlier seen that 22 kilo ohm is suitable. So we have connected 22 kilo ohm here. Now what we will do is let us do the frequency response. So theoretically the gain has reduced because of this feedback, but the bandwidth will increase. So let us go ahead and check that. For that, we are closing this, then simulate analysis, and then AC analysis. So all of you should remember that while you are doing AC analysis, this simulation should have been stopped. We have to double check that this has stopped, otherwise this will not work. So let us go for simulate, and then analysis, AC analysis, and then the parameters are according to what we have already said. Then let us go for output. Output is V6 by V4. Output is V6 by V4. The same previous values are already existing. So let us go for simulate. And then let us repeat the same process which we have done earlier. Right. So let us first bring this one, this particular box here, and then let us zoom in and see the cursor names. So this is second cursor, right click, go to next Ymax, and then right click, set Y value towards right, this one. So here earlier gain was 36, now it has dropped to 30 because of feedback. So 30 minus 3 gives us 27. So I'm changing this to 27. Then we are clicking on OK. So the second cursor has adjusted itself at higher cutoff frequency. Then first cursor, again right click on this, go to next Ymax, right click on this, set value towards left, and let us change this to 27. So this one we are changing it to 27 because 30 minus 3 gives us 27, and we are clicking on OK. Now the first cursor is adjusted at the lower cutoff frequency, second adjusted at higher cutoff frequency. We remember that the gain was 30 dB, and then let us see what is the bandwidth. The bandwidth has increased to 2.1 megahertz. Previous case it was 1 megahertz. So theoretically, we are having a reduced gain and increased bandwidth for the current shunt amplifier, which we have just seen. So once again, I am zooming out, and for the current shunt amplifier, we have seen both the input and output waveforms as well as the frequency response. So next we will go for one more experiment. Next, let us go for the two-stage RC coupled amplifier. So let me close this one. Circuit diagram is very simple. So first we have to go for one stage C amplifier. For that we have to remove this one. So I'm clicking on this resistor, then delete button on the keyboard. So this is the CE amplifier. To this we have to add one more stage of CE amplifier. So what we will do here is, first let us delete this particular oscilloscope. We can connect later on, so I'm deleting this one. Then what we will do, I am selecting this particular structure here, Control C and then Control V. Copy paste, simply copy paste, and then we are placing it here. Now we don't need two capacitors, so let me delete this one. I'm deleting this one. Let us align this properly. So first let me delete this line. I'm selecting that and delete button on keyboard. Then let us place this one properly here. I'm clicking on the screen. Now we don't need two VCCs. So let me delete this one. Directly you can join this point here. If you're not able to join, you can click Control G. You will get a node. You can place that here. And then from that point, you can join here. Next, this one has to be connected to the base of the transistor. So let us connect this one here. And then this point you can connect. I'm clicking escape, connect properly. This point I'm clicking. Then one more click here. This is connected. Then let us remove the bypass capacitor at the input side. We have removed that so that the gain is not going out of control. Okay. Then now what we will do, let us connect the oscilloscope. Okay. So we can remember that the fourth one here at the right side is the oscilloscope. I'm clicking on that. Then one more clicking on the screen. Okay, we got this. Now let us connect this second one to the ground. I hope all of you remember the same as you have done in the previous case. Again, this second one we will connect to the ground, and this first one. So the second channel usually we connect to output. So this B we are connecting here and the output, and this one at the input. So I'm clicking on this, and then one more click here. Then let us connect this one here. So output is in green color. Sorry, the input is in green color. Let us change the output to blue color as we have done in the previous case. So we'll click on this. So change this one to blue. Okay. Then okay. So the output has changed to blue. Now what we will do, let us run this and let us see the waveforms. In order to see the input and output waveforms, I hope all of you remember, first we have to run this one, then double click on this. Here you can see the input and output waveforms. You can stop this simulation by clicking here, and then let us see the input and output waveform. So I am changing this one to 20 millivolt, then I am increasing this one, and then here we are changing this to say 2 volts. Fine. And okay, let us further adjust this one. Okay, so here we can see that the green one is the input and the blue one is output. Gain is very high, because of that the waveform is not exactly sinusoidal signal, but very much close to that, and this is acceptable. And here we can see that the gain you are getting is much more higher than the single stage gain. I hope all of you remember that the single stage gain in dB was 36. Now let us go ahead and see what is the gain we will get. So in order to do that, let us close this one. Let us go for simulate, and then analysis, AC analysis. These have not changed, so let us leave it as it is. Let us see what is the output terminals now. The input is V4, output is now actually V9. So let us change that, simulate, analysis, AC analysis, output, we will change it to V9 by V6. Okay, so output here, we will edit, we will select this, we will go for edit expression, and then let us change it to V9 by V4. Okay, we'll click on OK. So it has changed to V9 by V4. Let us go ahead and simulate that. So this is the frequency response curve that we got. Now let us do the same process which we have done earlier. We were zooming in. We are checking, this is second cursor, right click on this, go to next Y max. Okay, so this is the maximum gain in dB. Right click on this, and let us adjust to the higher cutoff frequency. So set Y value towards right, this one. So now we are getting a gain of 45. Earlier it was only 36. Two stages are giving more gain. And to adjust this cursor at the higher cutoff frequency, we have to do -3 dB. 45 minus 3 gives us 42. So we are changing this one to 42. And then we are clicking on OK. Likewise, let us adjust the first cursor, right click, go to next Y max, and Y value, set Y value towards left. We are clicking on this. Maximum gain is 45. Maximum gain -3 dB gives us 42. We are clicking on OK. Cursor 1 has placed itself at the lower cutoff frequency. Now the dx will give us the bandwidth. So the dx here, bandwidth is 37.15. Okay. Single stage gave us higher bandwidth, nearly 1 megahertz. Here the bandwidth is low, and that is usually the case. Whenever the gain is high, the bandwidth reduces. So our simulation results are matching our theoretical concepts. So now again I am zooming out. Next, we will do one more experiment just by editing this particular circuit. The next circuit that we will do now is the Hartley Oscillator. So let me close this. Now, Hartley Oscillator has one stage of CE amplifier followed by 2 inductors and 1 capacitor in the feedback network. So let us change this. We have to delete one stage. So what we will do, we will select all these components, and then let us click on delete. So the one stage got deleted. You can adjust this, you can click this one, you can drag it here, so that it is properly adjusted. This is fine. Okay, no problem with this one here. Now, for the Hartley oscillator, what we have is we have two inductors and then one capacitor in the feedback network. Then this is the amplifier block. So let us go ahead and let us connect two inductors and one capacitor in the feedback network. So for that, what we will do is we will select the two inductors. You have to click here, this one, and then in the basic we have inductor. Let us click on that. Then you can type 4M. We will take two inductors of same value, 4 millihenry, and then you can click on OK. So we got the inductor. Let us place the inductor here. Then one more inductor. So once again you can click on OK to get the one more inductor. Let us place that one here. Now let us select one capacitor. So we'll go for the capacitor, this one, and let us take a value of 0.01 microfarad. Okay, so 0.01 U. You can double click on this, and then let us place the capacitor here. Then let us close this one. Let us join all these components. Let me click this one here. So the two inductors you have to connect. Then this inductor end we have to connect to the capacitor. So I'm clicking here. Then one more click and joining this one here. You can adjust the capacitor. We'll drag that and let us adjust this one like this. This capacitor end has to be connected to the inductor. And usually this point is connected to the ground. So let us go ahead. Let us join this one here. Then let us connect this point to the ground. So for that, what we need to do is we have to go for this particular, okay, what I have done, I have clicked here, and then we will go for sources. Under power sources, we'll go for ground, we'll click on OK. So the ground, I am placing it here. Let me close this. We have to join this point here. And then, so this is the amplifier block. This is the feedback network. And what we need to do here is we have to connect this point here, and then we have to connect the output. So this point we have to connect here. So for that you can go for Control J. We don't have a node here, so Control J. Place the node here, and then now we can connect this point here. Okay. And oscillator is a circuit which generates output without any input. So directly we are seeing the output without any input. So let us go ahead and see the output waveform. So I'm clicking on this, then double click on this. So we are getting the waveform. Let us stop this one. Let us adjust this. So this is the waveform of the Hartley oscillator that we are getting. Next, let us convert this circuit into Colpitt's oscillator. So for that, let me close this. Colpitt's oscillator has two capacitors and one inductor. So what we'll do first, let me delete this capacitor. I will do Control C. I have selected this, Control C, Control V. So one inductor, we are placing it here. We have to join this point here, then this point here, and these two have to be capacitors, so I'm deleting this one. I'm also deleting this one. In that place, we have to connect capacitor. So let me go ahead and select the capacitor. Let us take 0.033 microfarad. So 0.033 microfarad. Let us double click on this. So one capacitor, we'll place it here. And then another capacitor, let us go ahead and let us place it here. Let me close this one. Let us arrange this properly. Okay, so I'm placing this one here. Then let us join similar to what we have done in the previous case. So I'm connecting this one here, these 2 points connected, and this one is connected here. It's okay if the connection is formed, no problem. Okay, you can do it as it is. Anyway, I have adjusted it again. Now you can click on this point and then you can join it here. Okay. So this is the circuit for Colpitt's oscillator. What we have done, we have taken Hartley oscillator, and Hartley oscillator we had 2 inductors, 1 capacitor. We have changed it to 2 capacitors and 1 inductor. Let us go ahead and run this. So I'm clicking on this, double click on this. Let me stop this one. Let us adjust this output to AC. Both you can change it to AC. Then you can see the waveform. So this is the output of the Colpitt's oscillator. We are getting somewhat close to a sinusoidal waveform. The next circuit that we will be doing now is RC phase shift oscillator. So let us close this waveform. Then what we need to do is we need to delete this feedback network here, which corresponds to the Colpitt's oscillator. So I have selected all this. Then delete button on the keyboard. Then what we can do is you can also go ahead and delete this capacitor. We don't need this one. So I'm deleting this. RC phase shift oscillator has 3 stages of RC network. So let us go ahead and draw that. So I'm clicking on this, right? And let us take the 3 capacitors 0.001. Let us take, so double click on this 0.001 microfarad. Let me place, say, first capacitor here. Then okay. One more capacitor, let me place it here. Then once again, one more capacitor, let us place it here. Then we have to select 3 resistors. We are going for a basic and a resistor. Let us take 10 kilo ohm. So 10K, double click on this. Control R. Let us place the first resistor here. Then once again, okay. Once again, Control R. Let us place the second resistor here. Then once again, okay. Once again, Control R. Let us place the third resistor here. We can close this. Now let us join, say, first this point here. Second, capacitors. Let us join the capacitors. Next, let us join this point here. We can join this point to ground. Then this resistor we have to connect it here. This one here. Then this point we can connect here. This point here. So now we are ready with our RC phase shift oscillator circuit, which has 3 stages of RC network: 1, 2, 3. Okay. So this label doesn't matter. You can take R1, C1, R2, C2, R3, C3. It doesn't matter in what order they are. But this is the general structure of the RC network. Label doesn't matter. Okay. So next, let us go ahead and simulate this. I'm clicking on this one. Double click on this. Let us stop the simulation. Let me adjust this one. Let us also adjust this one. So we are not getting any waveform here. The reason is we have connected the amplifier block feedback network, and this point has to be connected back to the output. So we have not made that connection. So let us go ahead and make it. So for that, first Control J. We'll go for Control J. We'll place the node here. Once again, I'm going for Control J. J for junction. Let us place. So first we have to stop simulation, otherwise it doesn't work. So we are stopping the simulation. Control J. Then we are placing this one here. Now click on this. Let us join it from the top. Okay, let us go ahead. We'll click on this one, and then this point. Let us join it here. Now let us go ahead and simulate this. So we are clicking on this. Double click on this. Now this is actually very high voltage, so let us go ahead and reduce this one. Now here you can see that we are getting the waveform, so let us stop the simulation. Let us adjust this one. Let us click on this. So we are getting proper waveform here, as you can see. Okay. Then additionally, what we can do is we can find out what is the time period here. Then we can do the theoretical calculation of the time period using the formula of frequency for all the oscillators, and then you can match the theoretical and practical values. So in this manner, you can quickly complete 6 simulation experiments within 1 hour. As a continuation of this, what we will do next is we will do the same experiments in hardware. So we will see how we can actually simulate 12 experiments with the same CE amplifier block as common, and just modifying the remaining parts of the circuit will give us all the 12 experiments we can complete in very less time. So go ahead and enjoy your simulation and hardware experiments. Have a good time.